Hello everyone, and welcome to this video in which I'm going to be discussing a small topic, small concept inside the topic of permutations, combinations, and probability. I have been wanting to discuss this multiple times inside the classroom as well, to say with my students, but I didn't see till today much relevance with respect to this particular concept in order to solve questions in aptitude-based examinations like CAT, GRE, or GMAT. But increasingly, I'm coming across some questions which I feel that students will become more comfortable with if they have a proper sense of understanding of what mutually exclusive and mutually independent events are. So, the concept actually deals with the confluence of set theory and probability. So, I will try to throw some light and provide some amount of clarity on these concepts particularly. Hope it might be useful not just to solve questions of this particular type where these concepts are required, but also in general in getting a broader sense of understanding of what kind of relationships are possible between events. So before we start though, because this is an in-depth concept inside the topic of probability, so I need to give you a bit of background. I'll go through the very, very basics of a few things. Like I'll talk about what are permutations and combinations first. Then I talk about two very, very important rules called the AND rule and the OR rule, around which everything inside the topic of permutations and combinations and probability revolves around. Then I talk about the absolute basics of probability. Then I'll discuss what exactly is the meaning of exclusive and independent events and what other kind of events are possible related to exclusive and independent events respectively. And finally, we will solve one single question in this video at the end to gain some amount of clarity about where is it relevant for us to understand the difference between exclusive and independent events. Right? Okay, so with this clear, let me start off by talking about permutations and combinations, and I'm not going to solve any questions here. I'm not going to go in depth into concepts. I hope all of you are already clear as to what is the meaning of permutations and combinations and what are these and why do we use this. So just to give you a very brief summary of what this topic is all about, this topic helps us count the number of ways in which an event or multiple different events can happen. Right? It also helps us find the number of possible arrangements and the different number of ways that we can select a small subset of objects from among a larger set of objects. And this also provides clarity on how to treat identical objects and distinct objects when it comes to arrangements and selections. So permutations and combinations are actually an extension of basic counting. So it's counting how many ways can an event happen, how many different arrangements between objects are possible, and how many different ways can certain number of objects be selected from a larger number of objects. Right? Similarly, let me move on and let me talk about and give you a basic understanding of what the AND rule is. AND rule is one of the most fundamental rules which everything inside the topic of permutations, combinations, and probability follows. So the AND rule states that if I have multiple different events, and if all of the events are happening together, like event 1 and event 2 and event 3 and event 4 are all happening, then the number of ways that all the events can happen together is the product of the number of ways in which the individual events can happen. Let me give an example. Suppose you're getting ready for a job interview. You have taken a shower, you have worn a shirt and trousers and shoes, and you're almost ready to leave when you realize that I need to be dressed a bit more formally for this particular interview. So you decide to put on a tie and a suit. Now the tie that you have, or the ties that you have, are of two colors. So you have got, say, a red tie and a blue tie. Okay. So you only have a choice among these two ties. And the suits that you can wear, there are suppose three different colored suits that you have. You have a black suit, a gray suit, and a beige suit. Now the question is, how many different outfits can you now put on in order to go to the interview? So how many different outfits can you put on? The answer will be 2 into 3, 6 different outfits. Why multiplication? Because you're going to wear a tie and a suit for the interview. Okay. And for every single type of tie, you have got 3 different types of suits, which means that you can wear a red tie and a black suit, a red tie and a gray suit, and a red tie and a beige suit. Or you can wear a blue tie and a black suit, a blue tie and a gray suit, a blue tie and a beige suit. So for every tie, you have got 3 suits. So which means for 2 ties, you have 2 into 3, 6 different possible outfits. This is what the AND rule states, that if I have got 2 different events or 3 different events even, and event 1 can happen suppose in n ways, event 2 in n ways, event 3 in n ways, that the number of ways that event 1 and event 2 and event 3 can happen is in n into O ways, right? So this is the AND rule. And just like that, we also have the OR rule. Suppose you're still going for the job interview, you have still put on a shirt and a pair of trousers and shoes, and then you want to get dressed a bit more formally. But you realize that a tie and a suit becomes too much. So you decide that you're either going to put on a tie or a suit, right? So now you still have two different colored ties and suits of three different colors. And you decide that only one of these I'm going to wear. I'm going to either wear a tie or I'm going to wear a suit. I'm not going to wear both, because if I wear both, then it's going to become too formal for the interview. Then how many different outfits can you wear now? That will be, you have got 5 different outfits now possible for the interview. Why? Because you can either wear a tie or you can wear a suit. So you can either wear a green tie or a blue tie, or you can wear a black suit or a gray suit or a beige suit. So when events are joined by the conjunction or, then the total number of possible outcomes for that event will be the sum, the addition of the number of ways in which the individual events can happen. So if I've got 3 events, event 1, event 2, event 3, each can happen in M, N, and O ways respectively. So the number of ways in which event 1 or event 2 or event 3 can happen is in M plus N plus O ways. So these are the AND and the OR rules. And just to summarize quickly, why I'm talking about these rules is to tell you that AND implies multiplication. When you join a set of events by the conjunction AND, you will multiply the number of possibilities of every individual event. If you joined the events by the conjunction OR, you will add the number of possibilities of each and every individual event. And a very, very important thing to note here is that the AND and the OR rule are universally true. Any time you want to calculate the number of ways in which a particular event or multiple different events can happen, you can always turn to the AND or the OR rule. And this also holds true for probability. Even when you are calculating probability, the probability of event A and event B happening, or probability of event A or event B happening, will also always follow the AND and the OR rule. Or will they actually follow the AND and the OR rule always? Whether, when I'm saying it's universal, does it stand only for permutations and combinations, but is it also going to be true for probability? That is what we are going to be finding out further on in this particular video. Right? Okay. Now let me talk about probability. Right? I hope all of you know what probability is. Probability is always calculated as a ratio. It represents a mathematical value for the likelihood of an event happening. How likely is an event to occur? Right? And it's always calculated as a ratio of number of favorable outcomes of a particular event by the total number of possible outcomes of the event, right? I hope everyone knows what is probability. And also it is very common knowledge that the probability of an impossible event is 0, and the probability of a certain event, which will definitely happen, is 1, which means all probabilities will lie between 0 and 1. You cannot have probability of any event or multiple events happening to be greater than 1 or less than 0. If this is clear, then with this basic understanding, let's understand what is meant by mutually exclusive and mutually independent events. The mutually exclusive events are those events which can never happen together, which means if one happens, then that will not allow the other event to happen. So only one of 2 events can take place. Then the 2 events are said to be mutually exclusive events. And mutually exclusive events are part of the same probability superset. Now, what this means, we will look at in detail with, say, by using an example, but we'll just wait for a bit for that. But for now, just understand that mutually exclusive events are events which can never happen together. If one happens, then the other happening becomes impossible. And mutually independent events are those that do not affect each other's probability of occurrence. Which means if probability of one event happening is say 0.5 and a second event happening is 0.3, then even if the second event has already happened, even then the probability of the first event happening will still remain 0.5. So they do not affect each other's probability of occurrence. And mutually independent events, they belong to 2 different probability supersets. Okay. Now let me explain with an example. First, let me take up mutually exclusive events. Okay. So an example of mutually exclusive events are all the outcomes that are possible when you're rolling a fair die. For example, if say someone asks you to calculate or consider the probability of getting a 4 on the top of the die when you are rolling a die, and the probability of getting a 5 on the top face of the die when you're rolling the same die, then these two events are mutually exclusive events. Because if you roll a die and if you're getting a 4, you cannot get a 5, right? If you're rolling a die and you get a 5, you cannot get a 4. In fact, all 6 possible outcomes when you're rolling a die are mutually exclusive to each other, because if one event happens, it is impossible then for the other events to happen in that particular instance, right? And let's check whether the and the or rule apply to a set of mutually exclusive events or not. So let me take this example. What is the probability of getting a 4 or a 5 when rolling the die once? So probability of getting a 4 is 1 by 6, because one favorable event on total 6 different outcomes possible. Similarly, probability of getting a 5 is 1 by 6 as well. So probability of getting a 4 or a 5 when you're rolling the die once will be 1 by 6 plus 1 by 6 is equal to 1 by 3. So yes, or rule will be definitely followed. Okay. And if the question asks you, what is the probability of getting a 4 and a 5 in a single roll of a die? Then single roll of a die, of course, you cannot get both. So the probability of that will be 0. That will not be a question which will ever be posed, because if you're only rolling the die once, only one single outcome is possible. Right? That's why they're mutually exclusive events. But if the question asks you that if I'm rolling the die twice, what is the probability that the first outcome is a 4 and the second outcome is a 5? Then the first outcome being a 4, the probability of that happening is 1 by 6. And the second probability, or the second event, second rule giving you a 5 has the probability of 1 by 6. So 4 and 5, so 1 by 6 plus 1 by 6, or 1 by 6 multiplied by 1 by 6, 1 by 36 will be the probability that these events will happen one after the other. That in the first rule, you get a 4, and in the second rule, you get a 5. So yes, mutually exclusive events, when you're calculating these, they do follow the or rule and the and rule. Right? That's why I said that the and the or rule are universal. So far, it has turned out to be true. But let us go to the case of mutually independent events. And to give an example of this, let's consider flights. Right? Flights take off and land from several different locations across the globe every single day. Now, two different flights flying between two absolutely different destinations on a single day have got no bearing on each other's schedule. Right? So two different flights in two different parts of the world, whether they are going to be on time or not, they are mutually independent events, because one being on time does not affect the other flight landing on time. So I've taken an example of, say, a flight is traveling between Delhi to Mumbai, and we have got a second flight which is traveling between New York City to Chicago. Right? Now, these two events are mutually independent events, because if the Delhi to Mumbai flight lands on time, then the New York to Chicago flight landing on time, the probability of that happening will not change. Similarly, if the New York City to Chicago flight lands on time, that will not alter the probability of the Delhi to Mumbai flight landing on time. Right? So if I take this first set, okay, as a superset, as a universal set, or let me take this as a superset itself, because universal set will create a bit of a confusion. Right? So if I take the first set as the superset of the Delhi to Mumbai flight, right? Then suppose the probability of this flight being on time, okay? Let me write this, probability of on time, okay, is suppose 0.63, okay, and probability of it being late is of course the remaining, which is equal to 0.37. Similarly, if I take the second set as a superset of the New York City to Chicago flight, right? And suppose the probability of this flight being on time is, say, 0.45, okay? Which means the probability of this flight being late will be 0.55. Right? So they belong to two different probability supersets. Okay? Now let's check whether these kind of independent events follow the and rule or not. So what is the probability that the Delhi to Mumbai flight and the New York City to Chicago flight both arrive to their destinations on time? Then the answer will be 0.63 into 0.45. That both of them arrive on time. So and is following the and rule. Okay. So the Delhi to Mumbai flight and the New York City to Chicago flight, both arriving on time, will be 0.63 to 0.45. Right? But let's check for the OR rule. What is the probability that the Delhi to Mumbai flight or the New York City to Chicago flight arrive on time? So if I apply the OR rule there, then my answer should be 0.63 plus 0.45. But if I add this, you will clearly see that whatever answer you will get here, which will be around 1.08, that will be, if that is x, then that will be greater than 1. And we have already discussed that it is impossible for probability of an event or multiple different events put together to have a probability of greater than 1. So this result then becomes absurd, which means that the OR rule does not hold true when it comes to mutually independent events. Right? So how do we calculate the probability of the Delhi to Mumbai flight or the New York to Chicago flight arriving on time? So for that, what we have to do is, because we're calculating OR, so only one of them, either or, only one of them needs to arrive on time, which means I have to create two cases. First case is the Delhi to Mumbai flight arriving on time and the New York to Chicago flight being late, or the New York to Chicago flight arriving on time and the Delhi to Mumbai flight is late. This is how we have to then mathematically or linguistically reiterate the problem that we are solving. We cannot just say that what is the probability of the Delhi to Mumbai flight or the New York to Chicago flight arriving on time. We have to break it up into logical sense linguistically. And when we say that, we will say that either the Delhi to Mumbai flight arrives on time and the Chicago flight is late, or the Mumbai flight is late and the Chicago flight is on time. So when you add this up, or when you make the calculation now based on the AND and the OR rule, now you will get the correct answer. So directly, the OR rule will not be followed by mutually independent events. So even though I will still consider the OR rule also to be universally true, but it is not true in the classical sense that you just cannot replace OR with an addition. You need to use a bit of common sense in order to calculate the probability of mutually independent events, one or the other happening. Okay. Now, if this is clear, I hope this gives you clarity on what are exclusive and independent events. Now, if this is clear, then the existence of independent events should suggest that there must also be dependent events. So are there dependent events or not? And what's the meaning of dependent events? So the short answer to this question is yes, there are dependent events. Because there are independent events, of course, there will be dependent events as well. And there are three major kinds of dependent events. First type of dependent events is, suppose I've got two events. I'm only going to stick to two events. I'm not going to go to more than two events to discuss exclusive and independent events, because that gets a bit too complex for this video. So first type of dependent events is when both are completely dependent on each other. So event 1 and event 2 are completely dependent on each other. And a simple example of that are mutually exclusive events. Because if one happens, the other cannot happen. And if the other happens, the first one cannot happen. So they're dependent on each other happening. You can think of two dependent events like getting a head and getting a tail when you're tossing a coin. So these are completely dependent on each other. And an example of that is mutually exclusive events. Second type of dependent events are ones which are partially dependent on each other. Right? So which means that inside the same probability superset, you have got both the events, but they have an area of intersection, which means there is an area where both of them are happening together. But there is also an area where only one is happening and the other is not happening. So an example of two such events which are partially dependent on each other is probability of drawing one king or all heart cards while drawing three cards at random from a well-shuffled deck of cards. Okay. If you want, you can sit and calculate this. It's a very interesting problem. It will provide a lot of clarity on how to solve basic probability questions in aptitude-based examinations. But these are an example of partially dependent events. Why partially dependent? Because when I'm drawing three cards at random, there is a case in which all three cards are hearts and one of them is a king as well, because there is a king of hearts which is present. So that probability will lie in this area of intersection. So to calculate in this case, if I want to calculate what is the probability of drawing one king or three heart cards when I'm drawing three cards at random, then what I have to do is I have to calculate first the probability of drawing one king when I'm drawing three cards at random, plus the probability of drawing three hearts when I'm drawing three cards at random, minus the probability that one among the three heart cards is a king. Because when I'm adding the value of these two sets, the area of intersection of this Venn diagram gets added twice. So I have to remove that once. So this is where a bit of understanding of set theory also helps us solve probability questions like these. Okay. And finally, the third type of dependent sets is when one event is completely dependent on the other event, but the other event is independent of the first one. So an example, a typical example of that is winning the lottery, right? So if I take the two events, one is buying the lottery ticket and the second is winning the lottery. Right? Or I won't even say buying, because buying puts a kind of a say dilemma position, because someone else can buy and give you the ticket. Rather, I would say possession or owning a lottery ticket and winning the lottery. Now, winning the lottery is completely dependent on owning a lottery ticket, right? Without owning a lottery ticket, you cannot win a lottery. But owning the lottery ticket is independent of winning the lottery, which means that I can own the lottery ticket and me winning or losing is not going to affect the probability that I will own the ticket. So suppose you are going shopping, the probability of you purchasing a lottery ticket is something which is not going to get affected by whether later on you're going to win the lottery or not. But you winning the lottery is absolutely 100% dependent upon whether you have purchased the lottery ticket or not. So in this particular Venn diagram, B is the set of winning the lottery and A is the set of purchasing the ticket, right? So this is the third type of dependent events. In this case, what is the probability that you purchase a lottery ticket and you win? There you don't have to apply any sort of multiplication, because common sense suggests that purchasing a lottery ticket and purchasing a lottery ticket is already implied if you're winning the lottery, which means the probability of that will only be the probability of set B. Similarly, what is the probability that you will definitely not win the lottery? Is just the universal set or 1 minus the probability of winning the lottery. So the probability of purchasing a ticket does not even come into picture, because the event of winning the lottery is completely dependent upon you purchasing the ticket. Right? So these are the different types of dependencies. Now, why am I talking about all of this? What consequence is it going to be of in examinations like CAT, GRE, or GMAT, or any aptitude-based examinations? Generally, what I've observed is that knowing how many different types of events is absolutely inconsequential in basic aptitude-based examinations. Permutations and combinations and probability is one such topic in mathematics where if you think very logically, you can get to the correct answers of questions. And mostly by reading the question itself, you will be able to determine subconsciously whether the two events which have been mentioned are mutually exclusive, are they mutually independent, or are they mutually dependent? And then based on your understanding, I'm sure most of you will be able to come to the answer, arrive at the correct answer without drawing any kind of Venn diagrams, without even defining whether the sets or the events are mutually dependent or mutually independent or mutually exclusive. But still, I feel that having clarity on the different types of events can sometimes help us solve certain complex questions. I won't even call it complex, but tricky questions inside aptitude-based examinations. And one such example I have picked up for this video. So let's look at this question. The question says if the probability is 0.54 that stock A increases in value, and the probability is 0.68 that stock B will increase in value, then what is the greatest probability for the, or what is the greatest possible value for the probability that neither of these events will occur? Right? Now, generally speaking, two stocks increasing in value, commonsensically speaking, they seem to be independent events, right? And that is what most students will use subconsciously immediately to calculate the probability that neither stock A nor stock B is going to rise or is going to increase in value. But the question is not that simple, because there is a key word here to focus upon, which is greatest. The question is not asking us what is the value for the probability that neither of these events will occur. The question is asking us what is the greatest possible value for the probability that neither of these events will occur. And the question is also not specifying particularly, right? Explicitly, it is not specifying whether the events are independent or exclusive or dependent. So which means I have to consider all the possibilities and then figure out that among the different possibilities, which possibility will give me the greatest possible value for the probability that neither stock A nor stock B will increase in value. Okay. Now let's first go with the instinctive approach. Our instinctive approach says that neither stock A nor stock B increases in value, which means both stock A and stock B are independent events. So which means stock A should not increase in value. So that will be 1 minus 0.54. Okay. And stock B also should not increase in value. So that must be 1 minus 0.68. So this will give me the answer as 0.46 multiplied by 0.32. Whatever the values, I'm not going to get in the calculation. This is what we will get as the probability that neither stock A nor stock B will increase if they are independent events. But what if the events are dependent? Let's understand that if the events are dependent, and if you want to pause here after I ask a question, you can do that and think for yourself. If these two events are dependent on each other, then which of the three different types of dependencies will give me the greatest possible value for the probability that neither will increase? Is it the first type of dependency where they are mutually exclusive to each other? Is it the second type of dependency where they are partially dependent on each other? Or is it the third type of dependency where one is completely dependent upon the other? So if you want to pause the video right here, pause and think which of these will give me the maximum possible value of probability that neither stock A nor stock B increases. Now, if you have thought about all the three different possible types of dependent events, then you will realize that it is impossible for these two events to be mutually exclusive. Why? Because if they are mutually exclusive dependent events, then the probability of stock A or stock B increasing will be 0.54 plus 0.68, which is absurd, which is not possible because then the probability will become greater than 1. So they cannot be exclusive events, right? They can be partially dependent, or they can be one completely dependent on each other, or one completely dependent on the other. And of these, the probability that neither will increase will be possible only when one is completely dependent on the other. The smallest set should be stock A increasing, which should be a subset of stock B increasing, because stock B increasing has got more probability. In this case, neither stock A nor stock B increasing will be the outer area which is outside the probability of stock B, which means that the answer or the value for the probability that neither stock A nor stock B will increase will be simply 1 minus 0.68, which is equal to 0.32. Now, either this is the possibility or this is the possibility. The maximum probability when they are independent events is this. The maximum probability when they are dependent events is this. Now, of these two, which is greater? Definitely 0.32 is greater than 0.46 into 0.32, because anything multiplied by a fraction will decrease in magnitude. So 0.32 multiplied by a fraction, which is less than 1, will definitely be less than 0.32. So the answer to this question, that's why, will become 0.32 and not 0.46 into 0.32. Okay. In questions like these, it is imperative that we understand the different types of relationships that are possible between events, and only then can we get to a proper answer. So just wanted to discuss questions like these to give you a bit more clarity on the concept of mutually exclusive, mutually independent, and dependent events, so that if ever you come across a question like this, then you will know how to approach them and how to get to the correct answer. All right, so that's it, guys, for the video. Hope this was helpful. And we will be coming shortly with more such videos and more such concepts to give you clarity on multiple different topics of quantitative aptitude. Thank you for watching.